These videos are going to be looking at nested models, and they're pretty common when you're working with animals. And the example we're going to be looking at in these videos are working with lab rats. So lab rats are commonly used in biological and medical experiments because there's less ethical ramifications when you're experimenting on a rat. And let's say a university lab wants to determine whether two overworked undergraduate technicians, we'll say Jung and Janet, were performing procedures consistently with one another. If they're using two different techs, and they want to make sure that the results they're getting from each tech are consistent so they don't have to worry about which tech is performing the procedure. So if Jung and Janet measure protein uptake only once on each rat, what you were able to do was have one measurement variable, protein uptake, and one factor variable, the technician. So essentially, they're going to cut open these rats and then measure the protein that their kidneys are bringing in. And if that was the case, where we have one rat per measurement, and we have two factors, Jung and Janet, we would measure it with a one-way ANOVA. So Y would be the protein uptake of the jth rat under the ith technician. So our model would be the grand mean, the average protein uptake, plus the effect of the technician, and then plus the effect of picking that particular rat and anything else that's missing. Unfortunately, lab rats are expensive, so when you have to measure one, you have to kill them. So instead of measuring many rats, it'd be cheaper just to kill 3 rats and have them measure the location on each kidney 10 times per technician. And to make the suffering worse, as an undergraduate, they were forced to name each of the rats. So the rats got their own names. And since Janet only measures her 3 rats and Jung only measures his, what we have is a nested model with one fixed effect and one random effect. So Y is still going to be the protein uptake of the kth measurement on the jth rat measured by the ith technician. And it's going to be similar to our one-way model. We have an overall mean, mu, an effect of the technician, either Jung or Janet, and then an effect of the rat, and this symbol means this J isn't the same J across all the different I's. So when we're working with a crossed experiment, the same level J would occur both for Jung and Janet. So if they were measuring the same rat, so they both measured Dave 5 times, then this I would be crossed because it occurs both with Jung and Janet. However, each person only picked their own rat, so they didn't measure each other's. So that means rat 2 only occurs with Jung, and rat 5 only occurs with Janet. So we want to separate these, or indicate it anyway, by using this notation. So this is the jth rat nested inside of the ith technician. So that way we don't get it confused, because the second rat for Jung is different than the second rat for Janet. They're not the same rats. So we want to indicate that using this notation. And then we have our error terms. And these error terms are going to be about the rats themselves. Every time you measure the rat's kidneys, you're going to get something a little bit different, despite the fact it's the same technician and the same rat that's being measured. So this essentially is our error term for the technician, and this would be our error term for the rats. If we want to see if there's rat to rat variability as far as their protein uptake, we would compare A versus E. If we want to see if there's a technician to technician variability, we compare tau to A. And what the experiment looks like, if you kind of list it all out, Jung has 3 different rats, Arnold, Charlie, and Ben. Each one of those rats were measured 10 times. And then Janet has her 3 different rats, Frank, Dave, and Eddie. Each one of those were measured 10 times. Again, Jung only measures Arnold, Janet doesn't. Jung doesn't measure Frank, only Janet does. So even though these are the first rats for both Jung and Janet, they're different rats, so that's going to make them nested. These levels of the rat factor only occur with Jung, and these levels of the rat factor only occur with Janet. So that's going to make things a little more complicated to analyze than if we were working with a crossed model instead.